All right, hello. How's everyone enjoying the conference so far? Good? I really like Denver, I like our quirky hotel, I like the apocalyptic hailstorms, it's all just great. So as Will said, I'm a data scientist at Brandwatch, and one of my absolute favorite things to do is to stand on stages like this and just rant about data and social media and stuff. So I hope it's as enjoyable for you as it is for me. So what do I want to rant about today? I want to focus on the question of how we use data to make decisions. So most of the people in this room, that's your job. You're trying to make business decisions. You need to go out and collect some data to help you make those decisions, and then you need to turn that data into a technique for saying, yes, we should build that product, or no, we shouldn't target that group. So I want you to think in your own personal lives about some of the techniques and some of the questions that you ask when you're gathering data, when you're thinking about data, and when you're making decisions based on data. And what I will do is I'll start off by telling you a critical business decision that Brandwatch had to make about 6 months ago, which was, what should we order for lunch? So it was the holidays, most people were out on vacation, not too many people in the office. We just wanted to order some food. You know, it was cold and wintry in New York and all that. And so we had to decide between ordering sandwiches or ordering salad or ordering pizza. All right, so very critical decision, could compromise years worth of marketing and products if we get it wrong. And so what we did, like any proper data analyst would do, is we took a little poll of the office, and we found out that 40% of the office preferred sandwiches, 35% preferred salads, and 25% preferred pizza. So there we go. There's the data. The decision is really easy. 40% of the people want sandwiches. We should just get sandwiches, right? Done. But Brandwatch, we don't just go for the surface insights. We look more deeply into the data. And so we said, let's not just look at people's first place choices. Let's look at their actual order of preferences and see if that affects our decision at all. And what we found was that among the people who preferred sandwiches, their priorities were sandwich, pizza, salad. The salad people went salad, pizza, sandwich. And finally, the people for pizza ranked their preferences as pizza, salad, sandwich. All right, we have more data. We're getting kind of hungry, but we have more data, so it's good. All right, does this data actually affect our decision, or are we still just going to order sandwiches? I think this data actually affects our decision quite a lot, because now what we see is that while 40% of the people want those sandwiches, everyone else in the office freaking hates sandwiches. They're absolutely last place. So in an effort to please as many people as possible, we would have actually pissed off 60% of the office. So that's not good. All right, so that's a problem. We're not so sure about sandwiches anymore. So how do we make this decision? What should we do? Well, we're getting hungry, but we take these decisions very seriously at Brandwatch. And so, of course, we did what anyone would do, and we started consulting the mathematical economics and voting theory literature. And we found that there's actually lots of ways of taking these ranked preferences and turning them into decision strategies. So one is the simple plurality rules strategy. So 40% of the people want sandwiches, just make those 40% happy, and everyone else can go buy a salad somewhere else. That's how the US decides our presidential elections, right? If we have 3 choices, whoever gets the most votes wins. That's how our primaries work, too. I'll let you decide if that's working out for us or not. In France, they have a slightly different strategy. So what they do is they take the preferences and they eliminate the least popular choice, in this case pizza, and then they decide between the 2 remaining choices. In this case, more people prefer salad to sandwich than the other way around. So in this technique, we would buy salad. But there's even more ways to do it. There's more than 3, but there's tons of ways of doing it. Another one, and this is used by governments all over the world to decide on amendments to legislation, you do a little round robin. So you observe that more people preferred pizza to salad than vice versa, and more people prefer pizza to sandwich than vice versa, so pizza won't really make anyone mad. So maybe we should order pizza. All right, so this is kind of a disaster, right? So we have 3 legitimate ways of making a decision that are represented by governments and businesses all over the world. They're giving us 3 different answers. So this conference is about the truth, And it's not at all clear what the truth in this data set is. It's very simple. We're just trying to freaking buy lunch, and we're starving at this point. So what is the truth? How do we make this decision? And I want to emphasize that while the decision of what lunch to buy is extremely serious and the stakes are very high, this problem comes up in all sorts of decisions that we make all the time in our everyday lives. If you're a marketer and you're deciding which group to target, should it be moms or sports enthusiasts or, I don't know, whatever else, you're essentially asking the same question. You're asking, how do different people aggregate their preferences, and what decision should we make based on those preferences? Of course, this has serious consequences in electoral theory, even has consequences if you're an analyst in the audience. If you're trying to aggregate several different data sources together, the same version of this conundrum comes up. And so here's the bad news. There's actually no solution. So this is a theorem due to Kenneth Arrow, a Nobel Prize-winning mathematical economist. He proved this theorem in the 1950s, and it said that there's actually no one universal way of making this decision. No matter how you aggregate people's preferences, you have to make arbitrary choices, or you have to arbitrarily prefer the interests of one group or another. It's not that we're not clever enough to find a good technique, it's that there is no perfect technique. You have to make compromises. So that's kind of scary. It's kind of a disaster, as far as I'm concerned. Now, before I go on and get too exuberant about all this, I should make a confession that we don't actually do quite that much mathematical economics when deciding what to buy lunch. We were all just hungry, and so we bought sandwiches. And it's also possible, if I'm being completely transparent, I may have introduced all of this theory to swing the vote towards pizza, but neither here nor there. But this is actually kind of a metaphor for how we make decisions in the real world, isn't it? Right? In this case, we were hungry, but in your case, maybe you have deadlines. Maybe the campaign is next week. Maybe you can't afford to do all of the digging and all of the thinking that's necessary to summarize the data properly. So, what are some lessons that we can draw from this little toy example of buying lunch? I think there are two main lessons that I want to take away from this, and I want to explore in the context of other questions and other data sets. So the first lesson is that the truth can't be measured by numbers. What Arrow's theorem fundamentally says is that there isn't a sophisticated enough metric to aggregate real-world people's preferences between different choices. It's not a matter of finding a cleverer number or a cleverer formula. You have to use your values. You have to use other factors. You have to talk to people. You have to make compromises. The mathematics just isn't, numbers themselves just aren't a strong enough tool to help you make even basic decisions like this one. The second lesson is that decisions are more than data. Most of you are smarter than this, but there's this idea out there that if you want to make a good decision, all you have to do is gather more data. You have more data, and surely the answer will be somewhere in the data, right? The 50th data point is just going to say, like, I don't know, buy a cell phone or something like that, and that's what you do. But that's not how it works in real life. How you make a decision is just as important, if not more important, compared to the data that you use to make the decision. So these are the two lessons. But there's a perfectly natural question I'm guessing most of you are asking yourselves right now. Am I just a rogue mathematician ranting about theoretical points that don't actually come up in the real world, except possibly voting theory or something like that? Or is this something that is actually hurting us in the real world, that's actually causing us problems? And I think that the stakes in this discussion, the consequences of our failure to learn those two lessons, could not be higher. And I want to start with a little case study around what's called the compass algorithm. Has anyone ever heard of the compass algorithm before? Yeah, this is kind of a travesty, but it's not as public as it should be. So what the compass algorithm does is it takes a person convicted of a crime, and it's a little calculation, a little algorithm, which assigns that person a score from 1 to 10, which is supposed to be a prediction of whether or not that person would commit another crime again. So if you get a 1 or a 2, then the algorithm predicts that you just made one mistake, you've learned from your mistake, you'll do your time, and then you'll be out and you'll be fine, and that's it. You're low risk. On the other hand, if you get a 9 or a 10, then it means the algorithm thinks you're a career criminal, and you should be locked up, and you should be watched, and you should never be trusted again. And this score, so it's not just the COMPAS algorithm, there's dozens and dozens of these scores. They're used all over the United States, almost every state. These scores follow you throughout the criminal justice system. Judges use it to determine your sentence. Your parole officer uses it to determine what privileges and rights you should have and whether you should get parole in the first place. Social services use it to decide what social services you should have access to. So this score has really serious consequences on your life if you wind up part of the criminal justice system. And if that makes the hairs stand up in the back of your head, if that just makes you inherently nervous, it's probably because Tom Cruise told us all that this is a really dangerous idea in the movie The Minority Report. In that example, we had a perfect system for predicting crime, and yet it was still ethically questionable. There were still flaws. So all right, should we just take Tom Cruise's word for it, or should we actually go and look at some data? Well, some independent journalists at ProPublica actually went through and tried to measure this algorithm. By the way, a lot of the states that implemented the algorithm didn't actually measure it for 10 years. I think Wisconsin is using it, and they still haven't actually done a study on whether or not the algorithm is doing a good job of predicting whether or not people will commit another crime. So what they did was they went and they asked, how accurate is the algorithm? And what biases, if any, does it have? And they found that, in fact, the algorithm is only barely better than a coin flip. It's about 65% accurate in some data sets. And what's worse, when the algorithm makes a mistake, it makes the mistake in a biased way. If you are a white person who gets a 1 or a 2, then you're more likely to commit a crime than if you're a black person who gets a 1 or a 2. Similarly, if you're a white person who gets a 9 or a 10, it goes the other way too. So point is, it ends up, the actual consequences of this algorithm are that the color of your skin de facto can determine your sentence and your interaction with the criminal justice system. So in an effort to remove the human weakness and the human subjectivity from criminal justice systems, we actually inserted some of our worst biases under the guise of that objectivity. This isn't the only example. Several years ago, in 2008, the entire economy collapsed because of some financial mumbo-jumbo, right? We all remember that it was confusing, but to this day, I still barely understand what happened. The causes of this catastrophe were numerous and complex, but one core part of the story is that we used an oversimplistic risk metric to evaluate extremely complex financial instruments, just as we use an overly complex recidivism metric to evaluate what we should do with criminals. To this day, we measure teacher performance using these proprietary for-profit institutions that build these algorithms that try to measure the complex relationship between a teacher and their classroom. They try to take that relationship and they turn it into a single number which determines whether or not the teacher gets a raise, whether or not they get fired. And since these algorithms have been put into practice, there's been no discernible improvement in the actual educational outcomes, but there is some evidence that it's just making life harder for the schools who need the most resources. And of course, there's credit scores. So credit scores were originally designed to determine whether or not we should be trusted with a credit card, but now they're being used for everything. When you get insurance, when you get a home loan. It's one number that rules so many different aspects of our lives. Now, of course, in the marketing space, and analysis space and so on, I'm sure right now you're thinking of 10 different metrics that you use on a daily basis, and maybe you're not actually sure, does this actually work? Has it been measured? Can I really trust this metric? Will was telling me about the Net Promoter Score, which I think some of us use a lot, and I think he put it best when he said it's good because it's simple, but it's shit because it's simple. That's true for all of these scores. We're hoping for some simple number that's just going to make the decision for us. And in practice, this is leading to disastrous outcomes. So what should we do about this? I don't want to be only negative. Maybe we're all screwed. Maybe we should panic, move to the forest, live amongst the squirrels, collect flowers, make our own food. Doesn't that sound nice? I kind of want to do that. If this is how you feel about data and data analysis and artificial intelligence in the modern day and age, then I think this is actually healthy. I think this is a rational response to the way models and statistics and mathematics is used in the real world. It's a sign that your brain wants to think about these things critically and that you want to do a better job in your own lives and in your own jobs. And so I'd like to at least paint some picture of how we can move forward and do a better job, construct better metrics, make better decisions. One of my most deeply held personal beliefs, it's almost a religious conviction, is that human ingenuity can make our lives better. We can come up with ideas that fix even the stickiest and hairiest and hardest problems. And I also think that mathematics is one of the most important keys to that human ingenuity. So I'm going to take you through just a couple of mathematicians that I think can guide us forward and help us learn how to evaluate models better and make better choices. So I'll start in the early 1700s, before America was even a country, with the great Reverend Thomas Bayes. So he was a man of the cloth, but he was also an amateur mathematician. And he was fond of getting into these profound philosophical and theological debates with his friends at the pub, as we're all known to do. And one particular argument he got into is it possible to infer the existence of God just by looking at evidence around us in the world? Or is God just a purely metaphysical thing that we have to have faith in? So, like anyone would do, he went home and he tried to construct a mathematical model in order to win his bar argument. Of course, that's what we all do, I'm sure. And what he did, I can't really comment on whether or not he settled the theological question, but I can tell you that he came up with some of the most powerful tools for thinking about the relationship between data and truth that we have to this day. So as a very simple example of what he did, let's imagine you're walking along the street and you run into a coin, and you want to ask, is this a fair coin? So if I flip it 1 billion times, is it going to come up heads roughly 500 million times, or is it biased in favor of heads, or is it biased in favor of tails? All right, so one way you can answer this question is to do some deep metallurgical analysis on the coin. Another way is you could just flip it a bunch of times and see if you get heads too many times, or maybe you get tails too many times. If 5 out of every 6 coin flips come up heads, then maybe this is kind of a fishy coin, and maybe you should go try to swindle your friends out of some money with it. So that's a perfectly natural observation. We don't need Bayes to tell us that you can sort of infer that something is fishy about a coin just by flipping it. But what he did was he came up with a very precise mathematical technique for updating our assumption about the coin in response to new information. So we start with the assumption that the coin is fair because we don't know, and then every time we flip it, we look at the data we have so far, and we adjust our belief about the fairness of the coin correspondingly. So in this case, after these 6 coin flips, we might start to think maybe it's 5 or 10% biased in favor of heads at least. And this is a very simple idea. This was the early 1700s after all. They didn't have an insane amount of techniques. But it's lived on, and it's had some powerful consequences on the way that we work with data to this day. It's used to break codes. It's used to track the spread of diseases. One great example was a nuclear submarine in the 1960s lost contact with its handlers on the way back from spying on Russia or whatever it is that we did back then. So we just lost it in the Atlantic Ocean. And of course, the Navy wanted to go and find it, so they gathered all of the information, sensor logs and whatever they could get their hands on, about the fate of the submarine, and they actually used Bayes' ideas to build a probabilistic model of where they thought the submarine would be. And you can see that little red square kind of in the center of the screen. That's one of the red region. Those are the regions where the model predicted there would be a high probability of finding the submarine. And sure enough, the submarine was actually found in the southwest corner of one of those squares. So the model actually worked flawlessly. This was before we even had a lot of computing power to do these computations. So Bayes is a powerful tool for taking data that we find in the real world and making and updating objective belief systems about what that data is telling us. It tells us how to reverse engineer a model just by looking at the output of that model. So let's go to 1948 and meet Claude Shannon. Anyone heard of Claude Shannon or Bayes for that matter? Anyone? Okay, some of you, that's good. All right, well, I'm glad that we're all learning about these. So these ideas that these two people developed are behind the scenes in almost everything that we do with statistics and data in our everyday lives. In Claude Shannon's case, he was interested in a slightly different question. He wanted to know if you have a random system that's producing lots of data, and you don't know the structure of that data, how can you tell if there's some signal in it? Like, how can you tell if there's a little bit of bias, or how can you tell if there's some structure? How can you distinguish structure from complete noise and randomness? He was interested in this question for the purpose of trying to design more efficient communication systems. But his techniques have since been generalized and exploited in almost all areas of data science and statistics. So as a concrete example of how he thought about the world, he imagined taking a perfectly ordered deck of cards in the upper left-hand corner, and he imagined shuffling it just like our magician friend would do, except he's always up to some tricks, so maybe it's more random than what that guy does. But we keep shuffling the deck over and over again, and we track how random the distribution of the cards is as we keep shuffling. And what he realized is that this picture looks like the same pictures that physicists would draw when they're trying to understand the dynamics of a gas or a fluid. And indeed, the tool that the physicists use to measure disorder, the concept of entropy, he realized would exactly answer the question how to distinguish between a disordered system and a system with structure. As kind of a cute application of this, Shannon noticed that this idea of measuring disorder and information and structure is exactly the right tool for understanding why crossword puzzles are possible. You can think about it this way. If the English language were too structured, if there was too much order to it, if there weren't very many words, then it would be impossible to construct a crossword puzzle because the words would never fit together. On the other hand, if the English language were too random, if any sequence of characters could be a legitimate English word, then almost any sequence of letters you could draw on a 2x2 grid would be a legitimate crossword puzzle, and they would all be too easy. So it's only because the information theoretic structure of language, the level of disorder of the language, hits this sweet spot between order and disorder that we can all enjoy massive and difficult crossword puzzles on Sundays. I actually hate crossword puzzles, but some people like them. So this is pretty deep stuff. So on one hand, using Bayes, we can take data and we can build a model. We can reverse engineer a model which explains where that data comes from. And using Shannon, we can then take that model and we can find interesting structures that distinguish that data set from randomness. So how can we take these two tools and how can we combine them to solve all of the really hard problems that we're all thinking about in social media, in marketing, and whatever problems interest you? So here's an example. Let's say we take an image of a bird, like the one on the left. What we can do is we can use the insights of Shannon to extract interesting features of that bird, little line segments, little patches of color. And then we can assemble all of those features together, and we can use Bayes to infer what the underlying patterns that produce those patches of color and those lines are. And between the two, we can make a prediction of what is actually in the image. Is it a bird? Is it a person? Is it a cat or a dog? This technology actually works. There are businesses that are built around doing this kind of analysis. What if we could take these ideas and we could plug in social media posts that your customers put up on Instagram or Twitter, and we could answer questions about what their interests are, about what they think about certain products, what makes them happy or sad? What if we could design our products according to those interests that we can detect in that data? Here is a picture of the entire Wikipedia category graph. So when you go on Wikipedia, you search for something, it's got all these categories at the bottom. So what someone did was they took all of these categories and they arranged them into a graph structure, indicating the interactions and relationships in the large-scale structure of human knowledge. This is basically a picture of the hierarchy of all of human knowledge, at least all of it that's available on the English language Wikipedia database. What if we could take this structure and we could overlay it on the conversations that your customers or your partners are having on social media? What if we could understand the high-level topics of conversation that drive people to post things that make certain kinds of content viral and certain kinds of content stale? That would allow you to plan more efficient interventions into a conversation, to advertise your products more efficiently. And finally, what if we could take data about a social media conversation, or any conversation really, and what if we could look at patterns in the structure of that data over its history? So we would use Shannon to extract the signal from the random noise and the periodic behavior that's not interesting. And what if we could use this to detect interesting events that happen in a conversation and plan interventions that help us interact with the conversation better, and to resolve PR nightmares before they turn into whatever happened to United Airlines? So all of these tools are possible. This is not science fiction. These are all things that the Brandwatch data science team is exploring as possible product opportunities. But what they all have in common is none of them can be summarized by a single number. None of them generate a single snappy metric that just tells you how to make a decision. You have to be open to some complexity. You have to be willing to make a decision based on a picture or based on a complex relationship between topics. This is hard. But if we can do it, then this allows data and data science and statistics to turn into a spotlight instead of a straitjacket. So how do we get from where we are now to that future where data and data science is an ally rather than just something that confuses us and makes us want to move into the woods? Well, I'm going to just assign homework to everyone in this room, starting with myself. So I used to be a professor, as Will said, and I still have to assign people homework whenever I talk to them in a group. So my homework is to know you better. I want to know what decisions you're making, what data you're using to make those decisions, how that affects your businesses, and so on. I need to learn your domain better so that when I'm building tools, I know the compromises that you would want me to make, and I know the factors and the ideas that you think of as more important. And I also need to focus on the actual way that this is going to hit your bottom line. So it needs to not just be something abstract to me. I need to know what you're going to do with the answers that I'm trying to provide. I've talked to many of you already. I'm trying to get better at this, but this is something where this is an area where I need to improve. For you, I want you to do two things. So the first thing is I want you to own your own expertise. I know a lot of you have been in this business for years, in some cases decades. You are experts on social media. You are experts on marketing. You are experts on business intelligence. And when someone comes to you with a half-assed metric that tells you you should divide the number of followers by the number of retweets multiplied by the number of characters in the person's Twitter handle or something like that, I want you to push back and say, no, I know what I'm doing. That doesn't make sense to me. But I also want you to stay informed, because some of these tools are actually really powerful and really important. And we're at the crossroads between two different futures. One future in which we just surrender ourselves to the forces that want to take all of our data and crunch it in ways that we don't understand and make decisions for us because we don't know enough or we're not empowered enough to push back. The other future is the one in which we take ownership over these questions, the one in which we understand these tools and we understand how to use them to make decisions that make our lives better and the lives of our customers and the lives of our users. So this is hard. This is really difficult. I compiled a brief list of books, if you're interested, if you have some time to read, about the past, present, and future of data science. They will tell you what these models are, how they work, what the risks are, how to ask questions about what makes a good model and what makes a bad model. You don't need a degree in math to read these books. You just need some curiosity. And finally, please talk to me, ask me questions. I want nothing more than to work these problems out with you. All I have in this world is a cat and 2 degrees in math. So let's fucking do this. Thank you very much for your attention.